who can tell me what we were talking about? Anybody tell me what we're talking about? Yeah, Sarah.
Inverse functions?
Inverse functions, what about them?
Finding them and their properties.
Finding them, properties. I think what did we finished up with this, I think we finished up with this business of, if a function fails the horizontal line test, then it can't have an inverse function. Right? Do you remember that? Yeah, I think that's where we sort of closed up. Right. We finished up with the example of the sine, right, which very much spectacularly fails the horizontal line test. Okay. So again, we're talking about inverse functions, and we also, I think we already said that the graph of the inverse function is going to be the reflection. Right. We couldn't, otherwise it wouldn't have talked about the horizontal line test. Okay. So first, here are some concepts related to invertibility, invertible functions. Okay, so here's the first one. It's called one-to-one. So you have a function from A to B. If whenever A1 is different from A2, f of A1 differs from f of A2, we call f a one-to-one function. Okay. One-to-one. And it's often abbreviated as 1-1. It's also, there's another term for this, it's called injective. But I think one-to-one is more picturesque. Okay, so think about that for a second. Whenever A1 is different from A2, f of A1 is different from f of A2. What does that mean? What does that mean graphically? Or what does that mean about the graph? Whenever A1 is different from A2, f of A1 is different from f of A2. I want you to talk with somebody nearby about what you think this means graphically. Graphically. Okay, Reina, you had your hand up first. What?
So if you think of like A1 and A2 as as an x value, so like you would have A1
A1,
and
A2, different.
and then you put that into the function of f. A1 would spit out f of A1, and A2 would spit out f of A2. And since A1 and A2 aren't the same, f of A1 and f of A2 won't be the same either.
Okay, so f of A1 differs if you start off with different guys down here, you're going to end up with different guys up here. Okay, you start off with different guys, you end up with different guys. Okay, Win.
I was just going to add on to that, like it would fail the horizontal line test if it was not one-to-one, which means for functions have an inverse, it has to be one-to-one.
That's right. That's right. So this is how it's related to the inverse function, right? So if it's one-to-one, one will never have the following situation where you draw a line and it hits the graph in two points, right? Because if that happened, what would that say? That would say that your function has two values that have the same output, right? So if you're one-to-one, this is never going to happen. Okay. Being one-to-one, we'll never have this. Okay, so one-to-one means that will not fail the horizontal line test. Okay, so I hope you see, that this idea is pretty tightly, related with our topic. Yeah, Evan?
What is overinjected?
Oh, the function is 1-to-1, also called injective. So that's just another term. I think it's like the French term for it. But it's, people use it. Okay, so second idea. Definition F, again going from A to B. If, whenever, if for any B in your set, there is some A such that f of A equals B, then we call F onto, and the other term for this is surjective. Okay, so let me give an example. If you have f of x being 2x, so f of x is going to go from, say, the interval 0, 1 to the interval 0, 2. Okay, and f of x is 2x. Okay, and you notice that if I give you something in 0, 2, you can give me something in 0, 1 that gets mapped onto that, right? If I say the output is, I'd like you to hit the number 2, then you say what? Maybe you're just counting. Yes, 1. Right? You'd say 1. If I say I'd like you to hit the number 1, you'd say, put 1/2 into your function. That will give you the number 1. Right? No matter what number I choose over here, there's a number over here that gets mapped onto it. Okay, and so we cover the entire range here. Okay, so the picture is right. So here is the picture is like this. Right? We have 0, 1. Over here we have 0, 2, and basically we cover the whole range, right? Or if you're thinking about this as a graph, here's 0, 1 down here, here's 0, 1 down here, here's 0, 2 up here, right? And you notice that we hit every single value between 0 and 2, right? We hit every single value between 0 and 2. Right. So, for example, if I look at say 0, 2, 0, 4, f of x being x squared, right? Then this from 0, 2 to 0, 4 is onto. It's onto. Everyone getting this? Anyone confused? Anyone confused? Yeah.
Isn't this like the intermediate value?
Not exactly. Yeah, not exactly. I mean, the intermediate value theorem is talking about it's talking about the range of the function. Right? It's basically saying that there are no holes in the range.
But isn't it saying that there's going to be like a y value for every value between like the maximum and minimum?
Yeah.
And isn't that the same here because you're defining
Okay, so it's sort of related. Yeah, it's related, but not exactly the same thing. Yeah. You'll see what I mean in a second, I think. But yeah, it's certainly related. Okay. But if I said, so here's the sort of funny thing. If I say this into R, right, f of x equals x squared, right? Is this onto?
Can you just define what onto means here?
Sure. So onto means that if you take any point in the range, then you can find somebody in the domain that the function maps onto that point. Okay. So here, right, if you give me a 4, then somebody would say, well, just feed your function 2 and you're going to get a 4, right? If you say like a 1, then if you feed 1 into here, you get a 1 out, right? So whatever value, no matter what number I take in here, there's somebody in here that has that output. There's an input that corresponds to that output. What about something like this? Is this onto? No, right? Because I could say 10, right? There's nobody in 0, 2 that gets mapped to 10, right? So this function is a non-example, right? It's not onto. Okay. Okay, so here's the thing I want you to notice. Okay, is this function invertible? Think so. So here's the point. This function is invertible. This function f from 0, 2 to 0, 4 is invertible. And this function is actually not invertible. This function is not invertible. Right? From 0 to R is not invertible. And the reason is that you you can't find a function, right? Here you can find a function g going from 0, 4 back to 0, 2. Which acts as the inverse function, but here you can't find any function from R going back to 0, 2, right? Because there are outputs that have no inputs corresponding to them. Okay, there are outputs are so there are outputs that have no inputs corresponding to them.
In that case, wouldn't there be more than one input corresponding to them?
Actually, there's.
Because it'd be 2, like if you had 4 and b2, negative 2.
No. From 4, remember how it goes. Like if you start with 4, you say what input in 0, 2 corresponds to it.
Yeah.
Right. Well, 2 works, but we're not including the negative numbers here.
Okay.
Okay. So what I want to say is this, that f is invertible actually corresponds to f being 1 to 1 and onto. Okay. To be an invertible function, you have to be 1 to 1, but you also have to be on, and you also have to be onto. Okay. And that's one way of thinking about invertibility. I hope this is making sense. Anybody confused by this? The main part of invertibility is being 1 to 1, right? You have one guy here that gets mapped to you know, you never fail the horizontal line test, right? You never have anything like this, right? So, you know, you always have, you know, one value corresponding, one input corresponding to one output, right? Then you can get back from the output to the input, right? But the onto is also needed so that you don't, you know, have these guys that have nobody corresponding to them. Okay, so you want to have one guy corresponding to you. You know, you want to have at least one guy and only one guy corresponding to you. I probably should stop saying guy. Yeah, Evan.
So I'm confused how a one-to-one function wouldn't be onto.
Yeah. So look at this. Here's the example, right? So this function is 1-to-1. It's sort of in a silly way. That's probably why it's confusing, right? It's a 1-to-1 function, but it's not onto the reals. Right?
Why are you putting reals there?
Yeah. Why did? So that's true. You'd say, well, why not restrict it to actually its image, and then it will be onto. It will always be onto its image. So yeah. So that's true. You say, well, in fact, any 1-to-1 function is onto its image. So one can make it invertible by restricting the range. Restricting the range to the actual image. To that image. Right? So yeah, it's kind of silly. The onto part, you know, you could, you know, you'd say, well, what are you doing? Why did you say R anyway? You know, just take 0,4 and then it's invertible. Yeah, that's true. Yeah, but you know, but precisely, you know, your function's not invertible unless it's 1-to-1 and not. Okay, but yeah, that's a good point, and you know. Okay, let's get on it. Okay, too much. Okay, so for example, let's look at u to the x. Let's look at e to the x, right? This thing is a function from R to the positive real numbers. Right? Looks like this. Right? E to the x. It's an increasing function. A strictly increasing function. Right? And so it is 1-to-1. Right? It's strictly increasing, so whenever you have two values, the one on the right is going to be bigger. Right? So you never have to worry about two values being the same for an increasing function. Okay. So it's so it has an inverse. Right? So and it's also e to the x is onto its image, of course, R plus. So it has an inverse function going from R plus back to the reals, right? And you know what that function is called. What's it called? The inverse function of the exponential function? Natural log, right? Okay. Okay. I want to. Okay, so let's think about the graphs. graphs of inverse functions. Okay, so here's a problem for you to think. Okay, so say the point 2, 3. No. I'm sorry. Let me take it back. Okay, suppose f is continuous at 2, 3. At 2, sorry. I'm not going to choose a point. F is continuous at some x. Okay, so here's some x, and you know that the function is continuous there. Okay. Suppose also that it's invertible. And here's the question. What can you say? What do you think you can conclude about f inverse? Okay. So here you just have this one fact. F is continuous at this point x. F is continuous at this point x, and I'd like you to tell me something about f inverse. What do you think? Can you say, like, basically, can you say anything about f inverse? Can you say anything about f inverse? If you know that f is continuous at x, what do you think you could say?
If x is continuous.
Are you gonna say the answer, or are you gonna give an answer? Don't. I want you to think about it. Don't. I like Isaac, by the way. So, Isaac took martial arts from me last semester, so we're old pals. No, we're not pals, but at least we know. At least we know each other. Okay. Don't say anything, Isaac. Okay, talk to somebody nearby, and you can tell that person what you're thinking. Okay, so we're thinking about the graphs, right? We know that here's the graph. We know that if we're looking at the graph of f, at this point here, it doesn't jump. Okay, it doesn't jump. Okay, what can we say about f inverse, Isaac?
We can say that x. I was gonna say that f inverse could be differentiable as well. So if x is continuous, then it's differentiable.
No, if it's continuous, if it's differentiable, it has to be continuous, but not the opposite. Okay, what can we say about f inverse? What can we say about f inverse, Reina?
F inverse would also be continuous.
So f inverse will be continuous where?
At x, at whatever point that you're saying that f is continuous at.
So are you telling me that f inverse is going to be continuous
no,
right here?
I'm messed up.
Okay.
It would be okay. So since in the inverse x is technically y.
Yes.
So then the inverse of f would be continuous at y, or at x equals y.
What's y?
Whatever you.
F of
Yeah,
f of
f
x,
of x.
f of x,
Thank
yeah,
you.
at f of x, right? So this point here is x, f of x, right? You know that there's a corresponding point, right, at the reflection, right? You know there's a corresponding point for f inverse's graph, right? At f inverse's graph, there's a point there. The coordinates of that point are f of x, x, right? And you suspect that, in fact, it is true that f inverse will be continuous at the corresponding point, so at f inverse x. Part 2, suppose you know that f is differentiable at some x. Okay. Hold on. Think for, actually, don't even think too much. Just talk to somebody nearby and say, here's what I think is going to happen with the inverse function.
What's the question?
The question is, suppose the function is differentiable at x. What can you say? Can you say anything about f inverse? What can you say about f inverse? Anybody? Whoever wants to talk, raise your hands, please. Sarah.
F of x would be, or f would be differentiable at f of x.
You mean f inverse will be?
Yes,
Yeah,
f inverse.
So f inverse will be, in that case, f inverse will be differentiable also at f of x. And the idea is like, if you're differentiable here, then you're line-like, right? You're line-like. So you're well approximated by a tangent line. Well then, you're going to be well approximated by a tangent line over here also, right? When?
Can't you go even farther and
Yes.
say as long as the derivative of f of x is not 0, then the derivative of f inverse of x is 1 over the derivative of f of x?
Yeah, perfect. So in fact, there'll be a relation between these slopes, right? There's a relation between these slopes, namely that this, right? You've taken this triangle, and you've changed it into this triangle, right? So the slopes are going to be reciprocals of each other. Okay. So in fact, the derivative, the slope of the derivative at f of x will be 1 over the slope of f at x. Okay. Does that make sense? So yeah. So that's what we feel ought to be. Those are things that we feel ought to be true, and in fact they are true. Oh, I just erased it. Sorry. F of x is e to the x. Here we have the f inverse, which is the natural log function. Okay, so let me put up a theorem here. F is differentiable at x. So if f is invertible, f is differentiable at x forces f inverse to be differentiable at f of x with f inverse prime of f of x being 1 over f prime x. And the proof of this is easy. Okay, you can show this algebraically in the following way. You say, well, look, f of f inverse is what? if I take f of f inverse of x, what do I get? F of f inverse of x, these guys, x, right? You get x. Differentiate both sides. Differentiate both sides. When I differentiate x, what do I get? 1, right? When I differentiate the composition here, what do I get? Amani, what do I get? Don't know. It's a composition, right? F composed with f inverse of x. You differentiate it, right? By the chain rule, you're going to get the derivative of the first guy evaluated at the second guy, right? You get the derivative of the first guy evaluated in the second guy times the derivative of the inside guy. Right? By the chain rule.
Where did your F inverse go?
Oh, I'm sorry. This should be, well, the derivative of the outside guy evaluated at the inside times the derivative of the inverse of the inside guy. Okay, and so what does that tell you, right? That this and this are reciprocal, right? That f prime times f inverse x, f prime evaluated at f inverse x is f prime inverse x. And so you get that f inverse prime at x is 1 over f prime f inverse x. But wait, that's not what I said, right? That's not what I said. So, but it's okay. Let me, you can do it in the opposite order too. So you say f inverse of f of x equals x, and you differentiate both sides. So you get f inverse prime of f of x times f prime x equals 1. Right. And so f inverse prime of f of x equals 1 over f prime x. Okay. So you have these two formulas. They're basically the same formula. But this tells you the relation between the derivative of the inverse function and the derivative of the original function, right? That they are, when evaluated at the appropriate points, you get numbers that are reciprocal to each other. Okay. So if you ever forget, right, if you ever forget the relation, then just go to this. Okay. Go to the definition. Go to the definition of the inverse, and then just differentiate that, and then you'll get the relation out of it. Right. Right. You know that this is true, and then just differentiate it, and out will pop the relation. You just use the chain rule here. You know, the right side's, the derivative of the right is going to be 1, the derivative of the left, use the chain rule, and then the relation will pop out. Okay, so here's the example. Here's the example. F inverse x is natural log x. So what do we know? We know that the derivative of what's this gonna be? I'll let you work it out. Okay. The derivative, use this thing here. Use this thing here. The derivative of the inverse function. So, what's the derivative of the natural log? Right. The natural log is our inverse function here, and use this formula. Use the star formula to figure it out. Okay. It's just plugging things, evaluating and plugging things in. Let's take 1 minute, see if you can do that. Okay, turn to somebody nearby and talk.
Might just be because Alan has this basically the inverse of dx and so I feel like yeah, I don't
That's it. That's right. Okay, so using the formula, we had f prime evaluated at f inverse, right? Okay, well f was the exponential function. What's f prime? The exponential function. And we evaluated at ln x, right? So we get 1 over the exponential function evaluated at ln x. Right? Well, what's that? The exponential function evaluated at ln x is, it's going to be x, so we get 1 over x. Okay? So the derivative of the natural log is 1 over x. So you can use the formula. You know, maybe easier is even to think like this, right? Even easier is think the exponential function of the natural log is x, right? They cancel each other off. So you differentiate both sides. You get the derivative of the outside guy evaluated the inside guy times the derivative of the inside guy, and then 1 on the other side. So you get x times the derivative of ln x is 1. In other words, the derivative of ln x is just 1 over x. So this is basically starting from here and then just deriving instead of plugging into the formula. Either way, it's the same thing. Either you take the work you've already done or you redo the work. Okay. Okay, let me give you one problem to try. Suppose that f is invertible and that p point 2, 3 is on f's graph. And you know that f prime at 2 is 1/7. Okay, so you have 3 facts. F is invertible, 2, 3 is on f's graph, and f prime at 2 is 1/7. Give the equation for a tangent line, to f inverse's graph. Find the equation for a tangent line to f inverse's graph. So f is invertible. 2, 3 is on f's graph. And f prime at 2 was 1, 7. Give the equation for a tangent line to f inverse's graph. For the inverse function, that's right. Good. You're given information about f. I want you to give me the tangent line to a tangent line, the equation for a tangent line to f prime, f inverse, excuse me. If you can do this, then you'll understand a fair amount of what we're talking about today. Yeah. Oh yeah, yeah. Okay, so let's do this and then I'll hand it back. Forgot. Okay, so okay, so who would like to say? Amanda, you've been volunteering.
So I got y equals 7x minus 19.
Y equals 7x minus 19. 7x minus 19. I don't know. Is that right? So let's think of how did you get it?
I plugged in y minus 2 equals 7, parentheses x minus 3.
Equals 7x minus 3. Great. That's it. Right? Because you know that 2, 3 is on the graph of f, right? 2, 3 is on the graph of f, so you know that 3, 2 is on f inverse's graph, right? 3, 2 is on the graph of f inverse, and you know the slope there is going to be 7, right? F inverse prime at 3 is going to be 1 over f prime 2, that's to say 1 over 7. Right? You know that the slopes are reciprocal there, right? So it's going to be 7. So you've got this point, and you have the slope, and use the point slope formula. But then you change it to the slope intercept formula out of habit. So this minus the y value is going to be the slope times x minus x value. Okay, good. Okay, so let me hand back the exams.